Okay, classification of the wave. We can divide it into three ways to classify it. One is about the vibration. This one we learned in year 10 and I think it's from 4. Yeah. Okay, transverse wave is actually how the particle vibrate. This is direction of the wave travel. Okay, it will vibrating perpendicular 90 degree. For longitudinal actually is the sound wave. For example, sound wave. How they vibrate? They will vibrate in parallel way. Okay, this is the way how the particle vibrate lah. Okay, another one, how we classify the wave. We can classify in terms of their medium. Okay, for the mechanical wave, they need medium. They need medium. For example, sound. Okay, they need medium to travel. In vacuum, sound cannot travel. For EM wave, they are in vacuum, so no particle is needed. So no medium is needed in vacuum. So for example, the 7 wave lor. Okay, the 7 wave, radio wave, microwave, infrared ray, ultraviolet, visible light ray, X-ray, gamma ray. Okay. So today we talk about this energy transfer. It's new thing for us. Okay, it can divide it into progressive wave and stationary wave, or we call it a standing wave. Okay, so at here, what is this different? Actually, progressive wave, this first sentence is very important. Maybe you can highlight. Progressive wave is transfer energy without transferring the matter. They can transfer energy. But for stationary wave or standing wave, they actually no net energy transfer. Okay, but we learn about progressive wave first. Okay, we learn about progressive wave first. Next chapter, we learn about stationary wave lah. Okay, progressive wave, the pattern is like this. They can transfer the energy without transferring the metal. Year 10, we're also talking. We can have tie a ribbon at somewhere here. We can tie a ribbon somewhere here. Okay, ribbon somewhere here. Okay, somewhere here, ribbon. So when you shake up down, this is the way how you move. Okay, the particle moving, you will find that the ribbon actually still at the same position, just they move up down only. Okay, so this is the meanings that it didn't transferring the metal, but we cannot see the metal and we don't know where is the point. That's why we tie a ribbon at here. We tie a ribbon at the same position, and then we see. We'll found that the ribbon move up down. The ribbon doesn't transfer away. So we understand that the energy transfer from our hand, okay, transfer to the spring until the end. In moving, the energy is transferring. But the ribbon at certain position actually still there without transferring the metal. Okay. Progressive wave can be in the medium or can be in the vacuum. So for progressive wave, it can be the water, the light, the EM wave, the sound. No problem. Okay, they all are progressive wave. Okay, next here. Progressive wave transfer energy from one position to another one. This one, that's why we keep on repeating, is transfer energy. This is opposed to standing wave. Here. This different progressive wave is different with the standing wave because standing wave is no net energy transfer. Okay, they will oscillate fixed notes and empty notes. After that, when we study about standing wave, actually the wave will be something like this, then this. Okay, something like this. Okay, then they hit the wall, maybe hit something. They will reflect it. Something like this. Too ugly, but it's okay. Okay, so at here they will form notes. Note. So here, anti-notes. This one we will learn. Okay, right now it's just like introduce a bit to let you know. So they will oscillate like this, up, down. Okay, here, up, down. So this is called stationary wave, or we call it a standing wave lah. Okay, energy. See, I keep on repeating. Okay, progressive wave is energy transferred through oscillations or through vibration. So how we see the progressive wave, we can using the ropes or spring. So it goes to page number 2. We can using the ropes or spring to showing the progressive wave. Okay, so at here we can know that progressive wave, it can be happen in transverse wave or longitudinal wave. This is what I told you just now. They will move, you see how they move. The wave travel in this way. Okay, the particle travel up, down, up, down. They are 90 degree. Oscillations or vibration are perpendicular or parallel to the direction of wave travel. So for transverse wave, it will be 90 degree. For longitudinal wave, it will be parallel. Okay, so recall a bit what we have learned in year 10. So for transverse wave, we will form crest. This one, the peak point, we call it as crest. Okay, the bottom part, we call it as trough. Trough. This is crest. Okay, crest to crest, you can label in your worksheet also. Crest to crest here, this is called wavelength. Or trough to trough is called wavelength. So for transverse wave, actually can be sound wave, not sound wave, sorry, it's water wave, light wave, or any EM wave. Light wave is included in the EM wave lah. Okay. In year 10, we learn. Okay, I will using slogan to remember the 7 EM wave. Okay. Ramly makan Indian vegetable untuk ex-girlfriend. So I will remember all 7 EM wave. All they are belongs to the same family member. Okay, they were having the same family. They are under the same family member. So they all belongs to the transverse wave. Okay. Longitudinal wave is we will form two regions. One is called compression. If they are very packed to each other, the particle they are close to each other called compression. So this is compression, compression, compression. Those are very far away from each other. This is called rarefaction. Okay, so compression to compression or rarefaction to rarefaction, this one we say this is a wavelength, one complete wavelength. Okay, example for this longitudinal wave is sound wave. So for progressive wave, it can be a progressive transverse wave. It can be progressive longitudinal wave. Okay, so we look at two simple example of the past year question. This is 2022. Which statement about progressive wave is correct? Can you try and then you type your answer in the chat box? Oh, Prasan very fast, huh? Yes, correct, Prasan. Yes, Wesley, correct. Vashini, correct. Fawal, correct. Good job, dear. Answer is donkey. Okay, they are always transverse. No, it can be longitudinal also. Okay, it can be. They can only in solid, not liquid, not no, it can be in solid, liquid, or gas. Okay, decrease in frequency as their speed increases. No, frequency does not. It's independent on the medium. Okay, so it doesn't affecting frequency should be unchanged. So answer is donkey. Okay, what is progressive wave? It travel and transfer energy away from their source. That's why the wave move from left hand side to the right hand side. Okay, so number 2, which statement is correct for all types of progressive wave? Okay, try. Tony is D. Tony, are you went for dating last week? Dating, that's why absent. Prasan, yes. Wesley, yes. Okay. Vashini, yes. Manjo, yes. Wesley, yes. Okay, so Tony, last week you absent, right? Actually, if not mistaken, you're trying to go to the Google Drive. I think you should be able to access all the video. Okay. Kai Qian, D correct. Jia Han, Y is B is wrong. Okay, Y is B is wrong. Okay, dear, here. We go one to one now, okay? Your friend asking why B is wrong. Okay, Ripple tank. Ripple tank is only demonstrate water. Okay, they can demonstrate in Ripple tank. It only demonstrate water. Then how about light? How about sound? Okay, so not only water, but we also got light and sound. So they can be demonstrated in Ripple tank. Is only part of the wave can be shown by Ripple tank only. Okay, peak to another trough is half wavelength. Okay, peak to peak is one wavelength. Okay, peak to peak is one wavelength. They say that equals to a wavelength, but peak to trough here actually is half wavelength there. Half wavelength, okay? So they consist of vibrating atom. No, only, okay, this one is only for sound. Because sound, it need atom, it need a medium. Okay, EM wave does not need a medium. EM wave does not need any atom or medium, okay? So they consist of vibrating atom. This is only true for sound wave. Only true for sound wave. But others wave, light no need atom. They also can transfer energy. Okay, is it okay? Jahan, okay? Okay, like boys and girls, we go to your page number 3. If no question, then we go to page number 3. There is a button to react. You react, then I know that everybody okay, then we go. Give me reaction so that I can continue. Okay, dear here. Actually, this one nothing to say because we learn. Okay, just the question become harder only. Okay, we got two graph, displacement time graph and displacement distance graph. Okay, so at here from this displacement time graph, we can know two information. One is call period, because this is time. There, this is time. So from the time one complete wave, time taken for one complete wave, that is period. Okay, time taken for one complete wave is called period. One complete wave, I want to emphasize at here. One complete wave. Okay, we got 4 ways to determine. One is like this. This is one complete wave. Second, you can be opposite way like this. One complete wave. Yes. Number 3, crest to crest. Number 4, trough to trough. Okay, it's considered one complete wave. Okay, then we can have the period, we can find the amplitude. From the period, we can find frequency. Frequency unit is hertz, okay, it's hertz. Does this related to 2 pi over b equaling to the period? 2 pi over b is what? 2 pi over b, what is this b? Okay, here, displacement distance graph. Okay, here is distance. One complete wave. One complete wave, how far they travel. This is called distance. Distance it travel. So it's the wavelength, the length for the wave to travel called wavelength. Okay, so we know amplitude, we know wavelength, we can calculate the wave speed. Okay, then this is actually the knowledge is same as what we have learned, but we try with the A level question. Okay, the graph showing displacement distance graph, the period is 91 millisecond. What can be determined about the wave? Like boys and girls, look at it, A, B, C, D, and you try. Wesley, maybe you can share me. Is it your teacher worksheet or what? Maybe you can capture and show me. Okay, try question 1 and tell me your answer. Fawal, no. Fawal, try again. Jahan, try again. Wesley, try again. This is a progressive wave. Prasan, today I didn't saw Prasan. Washini, correct. Jore correct. Fawal correct. Okay, boys and girls, answer is A. Just now, few of your friends choose answer donkey. Okay, I know from here to here is your wavelength. This statement, no problem. This is your wavelength. But the problem is, it said this is transverse. How I know? It can be a longitudinal. Then this one it is a longitudinal. How I know? It can be a transverse one. Because progressive wave, it can be transverse, it can be longitudinal. Then how you sure? Okay. So at here, from this distance, okay, they say that the period is 91. So from period, you can calculate the frequency is 1 over period. Then period is 1 over 91 times 10 power of negative 3. You will get 11 hertz. Then V equals to F lambda. How fast the speed? Frequency is 11. Wavelength is 4 times 10 power of negative 2. So we will get 0.44 meter per second. Answer is A. This one confirm correct. Okay, C and D is longitudinal. Why I cannot say it is transverse? You say it is transverse. Why is not a longitudinal? It can be what? Okay. So number 2. Is it okay? Okay, then we goes to number 2. Is it okay, boys and girls? Okay. Here, dear. Transverse water wave. This one they tell you this is transverse. Okay, it's moving along the surface of some of water. This will cause the ball to move vertically. Remember, the ball move vertically without moving horizontal. This is the meanings that it gain the energy but without transferring the matter. So the ball only will go down, go down, and then go up to the same position. It won't go away. Okay, so at here the wave have a frequency. Okay, so they give you frequency. Normally from here we can calculate period lah. They give you period, normally we can calculate frequency lah. Okay, and amplitude is 0.7. The distance between the trough at here and the peak is 2.4. Okay, what is the distance traveled by the ball? Okay, how it travel? Go down, go down, go up, go up, go down, go down. How many times is go up or down? So we want to know. Okay, what we can solve is we find the period first. We find the period, yes. Period is equal to 1 over frequency. Okay, so I want you to calculate what is the period. Then I want you to think. From the period you think, okay? How many wave it need to go through with 20 seconds? How many complete wave? You have to find one complete wave. It takes how long the time? So 20 second actually how many complete wave it continue it moving? Okay. So from there you determine the distance it travel. Can you try number 2? Yeah, Prasan correct. So fast, Prasan. Wow, Manjo, yes, Manjo. Fawal, no. Fawal can try one more time. Tony, correct. Tony, correct. Washini, correct. Okay, so T equals to 1 over 0.2. So 5 seconds. One complete wave is 5 seconds. 20 seconds divided by 5, actually it will undergo 4 complete wave. Okay, so that means that at starting, it at higher point, one complete wave is actually is like this, dear. Going down, going up. Do you agree? Like this. This is one complete wave. So that means that one complete wave, it will go down, go down, go down again, go up again. So what I draw at here actually is one complete wave. The distance it travel for one complete wave. Do you agree? Do you agree like this? Okay, maybe I can draw like this. I cannot. Wait, go up, go down, go up, go down. Okay, roughly like this. So basically, my diagram is not good lah. Roughly only dear. Okay, for example, at here to here is one complete wave, right? So I go down, okay, then go down again, then go up. Wait, here. No. Okay, here go down, then here go down. Then here go up, then go up again. You get what I mean? This distance actually is one wave, one complete wave. How I travel. From crest, go down to trough. Go up to back to the crest. Okay. So at here, one complete wave, the distance travel, one complete wave. The distance travel actually is 4 amplitude, which is 4 times 0.7. So answer is what? 4 times 0.7, where 2.8 cm, right? Okay, here 4 complete wave, 4 wave. It will be 4 times 2.8. So your answer should be 11.2 meter. My drawing is too bad, but do you able to get my idea about one complete wave actually is going down, then going up, going up. It's called one complete wave. Do you able to get the idea? Okay. How the ball move down twice and up twice. You see, dear, from here, it go down, right? But of course, it doesn't travel horizontally, Wesley. Okay, it doesn't travel horizontally. It will go like this, going down, then continue going down, then going up, then going up. You get what I mean, Wesley? Prasan said initially the idea that I draw is good. I also don't know just now what I thought. But basically, the idea is here, lah. Okay, this ball is from crest to crest. So it crest to crest, so that means that from crest going down, you see, until the trough. Then after that, I come up again, go back to the crest. So actually, I undergoes 4 amplitude. Okay, I undergoes 4 amplitude. Is that clear? Any of you got question? Let me check the chat box. So the distance is not between the trough and the adjacent peak, but between the amplitude. No, how far it travel? You see the ball? The ball actually is only travel like this. Well, here. The ball actually travel up, down. It don't travel away. This is wave. But the ball only travel up, down. Okay, so it going from crest going down, so one amplitude, then going to the trough, another one more amplitude, then from the trough they go back again to the zero mean displacement, then going up again. So actually it's going down, up. It's 4 times. Okay, Fawa, okay? Okay, any other question? I try my best, okay, to explain for that. Okay, so if no question, we go to page 5. We go to page 5. Oscilloscope. Oscilloscope can be displays the pattern of the wave, okay, the pattern of the wave. But actually is here. It's showing the x-axis is the time. It can be show us the time. From the time we can determine the period. Okay, from the time we can determine the period. From the period we can determine the frequency, because frequency is 1 over the period. Okay, the y-axis, that means that this part. This part actually can determine the amplitude. Okay, can determine the amplitude. So from here, basically, you see this is one complete wave. Here, the x-axis from here, this point to this point, actually one complete wave. We can determine the period, t. What does it mean and what is the unit is used? Okay, it means that one division, it represents 5 milliseconds. From this diagram, it means that one division it represents 5 milliseconds. That means that from here to here, it's 5 milliseconds. So period, for example, we take this case as our example. Period is 1, 2, 3, 4, 4 division. So the 4 division times each of them is 5 milliseconds. So you get 20 milliseconds for our period. This is the way how we take information from the graph, from the oscilloscope. Okay, is it okay? Is it okay? If okay, then we try with past year question. Now it goes to next page, past year question. Okay, 2024. This is the wave showing by oscilloscope. Then you see, this is meaning that 1 cm represent 3.5 millivolt. What is the amplitude of the wave? So ask yourself. Okay, draw the horizontal middle line at here. Okay, from where to where is your, from where to where actually is your amplitude? So we label amplitude. This is amplitude. Okay, how many cm amplitude? Amplitude here in the diagram showing you 2 cm. Then 2 cm represent how many millivolt? So you know that 1 cm is 3.5. So 2 cm times 3.5 millivolt. Your answer should be 7.0 millivolt. You see, when we in the paper 2, we write our final answer, please. We don't write 7 millivolt, write 7.0. Two significant figure. Okay, so for this question, answer is C. Do you get the idea how we get the information from the oscilloscope? Yes or no? Give me reaction. Okay, Prasan say yes. Okay, Wesley yes. Okay, then we try with number 2. Question give you 2.5 kilohertz is frequency. So that means that from frequency, they're trying you to find period. From the period, I want you to think. Okay, one complete wave actually is from here to here. One complete wave. This is your period. You have to think the period, how you set your time base so that you can able to fix into this 4 box. Can you try, boys and girls? From the frequency, calculate the period. Then from the period, you have to think, hey, how can I fix it into my 4 box to show one complete wave? Yes, Manjo, correct. Baba, correct. How about others? Washini, correct. Prasan, no? Prasan, no? How about others? How about others? Frequency giving you 2.5 times 10 power of 3 hertz. So period is 1 over f. 1 over 2.5 times 10 power of negative 3. In 3, not negative 3. It's 3. Okay, so at here is 4 times 10 power of negative 4 second. Okay, let me check. Jore say, yes, Jore correct. So at here, we want to fix this 4 times 10 power of negative 4 in this 4 box. So that means every one box, every 1 cm, actually it should be 1 times 10 power of negative 4. Do you agree? Okay, 4 cm, actually we need to fix 4 times 10 power of negative 4 second. Then 1 cm, it should be 1 times 10 power of negative 4 second. Right? So it should be 1, 0. Okay, 1 times 10 power of negative 1 times 10 power of negative 3 second. Because the answer at here, they all milli. Or this one cm. So I'm trying to make it into milli. So it becomes 0.1 times 0.1 millisecond. Okay, this one. Milli. Okay. Then after that, Here combine, it will become every 1 cm 0.1 millisecond. So 0.1 millisecond per cm. Per cm, that means that every 1 second. Every 1 cm. Okay, every 1 cm. So answer should be A. Is that clear? 4 times 10 power of negative 4, you need to fix into 4 cm. So each 1 cm actually is 1 times 10 power of negative 4. 1 times 10 power of negative 4 actually is 0.1 millisecond. Can repeat from the 1 cm thing, 1 cm. Okay, here I repeat again. Because I know this is one complete wave. It took 4 cm to fit this one complete wave. The 4 cm actually 1, 2, 3, 4. One complete wave, 4 cm. 4 cm, the period is 4 times 10 power of negative 4. So I want to know 1 cm actually is how many seconds? Because in our time base, you see, in our time base, we will also always per cm, every 1 cm or every 1 division. We'll talk about 1 cm, what is the time? So at here, we do the same thing. 1 cm, what is the time I need to fix? Okay, I need to fit. So at here, 4 cm is 4 times 10 power negative 4. So 1 cm, I know is 1 times 10 power negative 4. Okay, then why I become here times 10 power negative 3 times 10 power of negative 1 is because here I saw the answer is in milli. I know that in milli, okay, so there will be times 10 power of negative 3. Okay, so at here, I trying to make it 1 times 10 power of negative 4. I trying to split it up. It become times 10 power of negative 3, then times 10 power of negative 1. Because negative 1 plus negative 3, I get back negative 4. This is your mathematics. Okay, so this part, it become milli. It become milli. This part become milli. Okay, then this part, 1 times 10 power of negative 1, this is become 0.1. So I know that every 1 cm, I need 0.1 millisecond. Now Wesley, which part? Still not clear? Is it you're confused because of changing at here? You get it, huh? Okay, boys and girls, we go to your page number 7. Goes to page number 7. Okay, can you try without guiding? Try it. You find one complete wave. What is the wavelength? Okay, then you have to think how you fit this into the oscilloscope. And then what is the period? Wavelength how many cm? Then you from there you guess how long the time for one complete wave. Prasan correct. Jore correct. How about others? Let me have a look. Vashini correct. Okay, dear 10 cm, 10 cm, how many complete wave? So at here, 1, 2, 3 and half. So at here, 3.5 wavelength actually is 10 cm. One complete wave wavelength is 2.86 cm. Now you have to ask yourself, One complete wavelength is 2.x6 cm. What is your period? Now you look at this. Okay, the period, the x-axis, the time-based part is 5 millisecond per cm. That means that 1 cm, 5 millisecond, right? One complete wave, you need 2.x6 cm. Agree? How many seconds you need? That is your answer. Because this is the wavelength for one complete wave. Then this time is the time for one complete wave also. So it's called period. So question asking you, what is the period? Vowel correct. Okay. So at here, you can using a mathematic wave ratio to solve it. At the end, you will found out that this one, 2.x6, actually they need 0.014 second. So which is donkey? Okay, we find out the one complete wave is actually 2.x6 cm, one complete wave. Then 2.x6 cm, how long the time it needed? We found out that it needs 0.014. Wesley, correct. D is correct. Okay, any question for this? If no, we are going to the question number 4. Give me reaction, is it okay? Papa said okay. Who else? Moni, okay, good job, Prasan, Manjo. Okay, like boys and girls, number 4, let you to think. You need to have some idea about this. Because this, the time base and wide-gain they set are not that nice, you know. It cannot display the whole wavefront. So I need you to think, your time base actually should be increased or decreased so that you can see the whole pattern. I want to see the whole pattern. No, this one that I draw is this. Prasan, this one. This is sinusoidal form. Wesley, which one? You give me two answer? The second one, no? First one is correct. First answer is correct. Tony, no. Tony, no. Let me have a look, Wesley. Oh, Wesley get the idea. Okay. How about others? Do you get the idea? Prasan, let me have a look. Prasan, correct. Prasan, correct. Okay, deal. Maybe I can trying to use some value to show you. Okay. Kai Chen, no. Can try one again. Fa Wang, no. Okay, it's okay. Maybe I can give you some value to have a look. Okay, from here to here is one complete wave. Okay, then here maybe we can put some value from here to here to here. Okay, actually I simply put some value lah. Let's say this is 20 millisecond. Okay, your time base, if your time base, let's say we set 1 millisecond per cm, that means that how many cm you need to display one complete wave? You need 20 cm. Do you agree? 1 cm to represent 1 millisecond. So now one complete wave is 20 millisecond. So you need to show 20 cm. But the problem is still, you see at here, Okay, let's say we set it to become higher time base. Okay, 5 millisecond per cm. Every 1 cm at here, okay, every 1 cm, it represents 5 milliseconds. So how many cm do I need? I need only 4 cm, right? So do I able to show with 1, 2, 3, 4? I already can show one complete wave. You get my idea? So we need to increase our time base so that we can display more wave. For this, is it okay? We need to increase our time base. So that means that we can display more wave. Is that clear? Is it okay, dear? Any question? Prasan, okay. Okay. So that is the same idea. Same idea as you are widen. You see, we cannot see. We cannot see. It doesn't show the whole part. So what should we do? That means that this one, every one division is too small. The value is too small. That's why it need a bigger diagram, bigger cm, bigger division to show all. So what should we do? Okay, we make this increases. That means every one division or every 1 cm, it represent a higher value lah. It represent a higher value. So that means that at the end we can showing you a smaller, okay, we can get a smaller something like this going down and then coming down. Okay, we can display. Oh my goodness. Like this. Like this. Idea actually is same like what I explained at here just now. Okay, if you using a too small the time base, actually you need more cm to display the one complete wave. Then since the microscope is very small, not that small but small, so how can I display if your value is so small? You need 20 cm to display all. Then we make it the scales increases make every 1 cm with higher millisecond. So we only need 4 cm to display. 4 boxes to display. Is that clear for this number 4? Answer will be donkey. Okay, Wesley said okay. Yeah, Jory correct. Okay, next, number 5. Oh, what is mean by frequency? This one is your year 10. Year 10, when we study about wave. Can anybody tell me? Type your answer in the chat box. Tell me what is means by frequency. Let me have a look. No, Fawal cannot define in this way, no. No, Vashini, this is called period. Time taken for one complete wave is called period. How many times a wave pass through a certain point in 1 second? Yes, Wesley? Prasan. Number of oscillation per unit time. Yes. Okay, number of oscillation in 1 second. Prasan answer is the best. Okay, so at here, number of oscillation, wave front, crest, trough, all can be. Okay, oscillation, or we say wave per unit time. Okay, actually it's 1 second. How many waves? This is called frequency. Period is the time. Time for one complete oscillation. Remember, period is time. But frequency is how many waves? Number of waves. Okay? So if okay, then we go to the next question here. Ashini, let me have a look. Yes, okay. My boys and girls, a loudspeaker, microphone, CRO, oscilloscope are arranged. Okay, so they were emitting a sound wave which is detected by the microwave and displays on the oscilloscope. Time base is 0.5 millisecond per cm. That means 1 cm, 0.5 millisecond. 1 cm represent 0.5 millisecond. Then why is 1 cm represent 0.20 volt. So this one is represent 0.20 volt. Okay, we read the next question. Can you calculate the frequency? Frequency, what should you do? Find the period. Period is from where to where? From crash to crash. This is called period. So you ask yourself, period, how many second, millisecond for one period? Then from there, using the formula, F equals to 1 over T. Do your calculation and tell me your answer. Wow, correct. Good job. Wesley, correct. What is a unit? Do not forget about the unit. Kai Qian, can try one more time. Wesley, correct. Prasan, correct. H is capital letter. Vashini, correct. Okay, dear all, here. How many cm? 5 box is 1 cm. So at here is 1 cm, 2 cm, 3 cm, and 4 cm. So in total is 4 cm. Okay, so period is actually 4 cm times 0.5 millisecond per cm. So per cm can cancel out. Okay, cm per cm can be cancelled out. Then after that, here we get, how many I get? 2 times 10 power of negative 3 second. Milli times 10 power of negative 3. So I get 2 times 10 power of negative 3. Frequency is 1 over T, which is 1 over 2 times 10 power of negative 3. So our answer should be 500 Hertz. Capital letter H. So this is the answer for the number 1. How you find the frequency. Is that clear? Is that clear, dear? Okay. Okay. So can you count amplitude? This one easier. Amplitude. Good job, Farwell. Prasan, correct. How about others? Amplitude. Vashini, correct. Wesley, no. Wesley, count properly. Count properly. Kai Qian, what you give me, the answer is in cm, not yet in volt. You have to convert it into volt. What is the amplitude? How many volt? Jore, unit. Magnitude is correct. Okay, so boys and girls, here to here is called amplitude. This is called amplitude. Amplitude, this is 1 cm, 1 cm. This is not yet 1 cm. This is 0.8. So in total from here to here is 2.8 cm. So you have to count properly. Okay, you have to count properly. Then here we know that every 1 cm is 0.2. So 2.8 cm times 0.2 volt per cm. So per cm and cm cancel. So I will get this one is 0.56 volt. Okay. Now this one actually the tricky part is you have to be careful. Actually not yet goes to 5 box. It's not yet goes to 1 cm. It's 2.8 cm. Is that clear? Okay, then we are going to enter the next part. Is it okay? Can I proceed? Okay, if I will say yes, Wesley, yes, Vashini, yes. Okay. So boys and girls, we comes to intensity and amplitude. Intensity and amplitude. Okay, we know that the progressive wave, they will transfer energy. The amount of energy passing through a unit area per unit time actually is called intensity. Okay, so at here the energy converting pass through a area per unit time, actually from here to here, E over T. E over T actually is power. So actually power over A is intensity. Energy divided by time is power. So that's why we get this formula. I equals to P over A. But I found out that actually we can remember in this way. Power is AI very powerful. Okay, AI very powerful. A times I become powerful. Or using nowadays we're using AI. Okay, intensity is power per unit area. Okay, so at here, what is the unit for intensity? Power is called what? Watt per square meter. Or we say W m negative 2. This is the unit for intensity. Okay, this is the unit for intensity. Okay, Wesley have to check. Have to check, is it provided in the formula list or not? Okay, the area passed through is perpendicular to the direction of its velocity. Okay, so next, this one is roughly can be like this, perpendicular. Okay, perpendicular to the area. Okay, then intensity will be decreases when they travel, okay, along. It will decrease, reason is because of the wave spread out. Maybe some of the wave absorb or scatter, okay, so the intensity will decrease, okay. As the wave spread out, the amplitude will decrease, so they can relate in intensity and the amplitude. They are directly proportional to amplitude square. So at here, if we want to make it become a mathematic, okay, we can write I give some constant value, a square. Okay, directly proportional, we can change it to become equal. This symbol can change and we add a constant value. It's something like we learn about Hooke's law. We say that the F is directly proportional to the extension. Your force increase, your extension will be increased. Then at the end, we get the Hooke's law. F equals to Kx. We add a spring constant for it. It's a constant value. So right now, actually, the idea is also the same. I is directly proportional to the amplitude square. So we can also give some constant value, constant number, yeah. Okay, to make it become I equals to constant, then A square. Okay, we look at this. We got two waves, P and Q, having same amplitude. Then the wave meet in the phase at point X. So initially, I got two waves. One is called P, amplitude. Let's say I give A. Then another Q, also amplitude A. At a certain moment, they meet up at somewhere here at point P. They will give a resultant wave. Okay, they move in this way and they move in this way. If you are graduate from SPM, we know they meet up. Okay, when they meet up, what's going on? The new wave, it will become double up. For those you are graduate from IG, it's okay now. You're trying to know something new. So when they add it up together, they become 2 ampere. Okay, they become 2 ampere. So at here, what they say, amplitude of wave P is double. Oh, okay. So right now we got another case. This one QP. P is double up. Okay, P is become 2 ampere. Then Q is only 1 ampere. Okay, Q is double up. Amplitude for P actually is 2A. So amplitude for Q is only A. Okay, roughly this is the idea. So initially, our resultant is 2 ampere. now we become how many ampere? We become 3 amp, not ampere. Why I say ampere? 3 amplitude, not ampere. 2 amplitude and 3 amplitude. Okay, because the P at here they become 2 ampere and 2 amplitude, P and Q. Okay, now they add it up together, they become double up with 3 amplitude. Okay, this is the case. Okay, now how we solve the question. For those you haven't learned, it's okay for the how they meet up, why we add it up together. This one in the next chapter, superposition, we will learn. Okay, they add it up, they meet up, then they will add it up together. Okay, what is the new intensity? Okay, the intensity is Ka square. So this one is original. We got I equals to K, our amplitude become 2A square, right? So we will get 4Ka square. Do you agree? This one is the original intensity. Original intensity. Okay, how about our new intensity? Now it's a new case. New intensity. Ka, our A is 3 amplitude. So we will get 9Ka squared. Do you agree? Okay, so I want to know my new intensity in terms of I. That means that I want to relate these two. I want to relate these two. In terms of the I, okay, to describe what is your new intensity. So what should I do? We can using the ratio I new divided by I. Then for 9 Ka square divided by 4Ka square. Ka square, Ka square we can cancel. Okay, then here I new actually is equals to your I move to another side. We will get 9 over 4 actually is 2.3 I. You get the idea how we solve this question? Right, boys and girls, digest a bit. How am I solve this question? Initially, same amplitude, when they meet up, the amplitude become 2A. So the intensity is 4Ka squared. After that, they say amplitude P double up, so it becomes 2A. 2A meet up with the QA, they become 3A. So your new intensity will increase because now our amplitude becomes 3A. So it becomes 9Ka squared. They want to find what is your new intensity in terms of Y. That means that they want you relate back with the original situation. So I'm using ratio to find it. 9 over 4, I get 2.3. The I bottom part, I move to another side. So I know that the new intensity actually having higher intensity than original, which is 2.3 times the original. Okay, digest, and then if okay, then let me know. Okay, Papa, okay, how about others? 2.3. 9 divided by 4, you get 2.3. 9 divided by 4 is 2.3. Actually, it's 2.25. Okay, we make it become two significant figures, so it's 2.3. It's okay, Prasan? Okay. Then, boys and girls, we can go to the next page here. Okay, a beam of light with power P has an area of cross-section A. The amplitude is X. Okay. The beam of light is then changed to 1 with the same frequency, but new amplitude become 4x. Initially, the amplitude is x. Now, new amplitude, it becomes 4x. Okay, the closed area, it become, new area become A over 3. Okay, A over 3. So what is the power? Power, just now I told you power, AI. AI is very powerful. So that means that we need to link with intensity. Now the problem is you have to find the intensity for original and intensity after. Okay, so intensity is Ka squared. Initially, this is the initial case. Here is initial case. Then this one is new. Here is original. Okay, original, our area is A. Then our original intensity is equals to Ka squared, nothing. Oh? So our original power is what? AI. Okay, your A is area. A at here is area. This A is called amplitude. These two A is different, dear. This is amplitude. This is area. They are different, although it's the same symbol. Okay, so this one A, don't move. Then this one is K. The amplitude at here, we substitute, it become x squared. See here? This is amplitude become x. Okay, amplitude become x. So at here, I put it here, x squared. This is called amplitude. This is called area. Don't mix up. They are the same, but same symbol, but they are different. Okay, so at here, I know that I get akx squared for initial. So we have to trying. What happened to your new? New, so you think k amplitude square. So I want you to think, what is this? And then your p new is a area new times new intensity. Area new, I can give you some hints, is A over 3. Then what is your new here? Do substitution into it. And then, using just now what I teach you, power of new beam, divided by power of original. So you're using the ratio, solve the problem, and tell me what is your new power. Same idea as just now, but I need to continue the step, like give the hints. So you find original, then you have to find new one. Okay, try it. Kai Qian, correct, Kai Qian. Fawa, correct. Washini, correct. Good job. So here I want to emphasize I equals to Ka squared. This is amplitude. Power equals to Ai. This is area. It's different. Wesley, correct. Okay, so since a lot of you correct, then we can try. So this one is Ka here, A here. The new amplitude at here actually is 4x squared. So it becomes 16kx squared. So I put at here 16kx squared. So at here 16 divided by 3 actually is 5.3 kx squared. So I put at here 5.3 kx squared. So the initial is a kx squared. So actually we can cancel. So what I get? P new is 5.3 P initially. Initially is power P. So it's equals to P. PO is actually P. 5.3 P. Answer is boy. Okay. These two questions we learn to using ratio. Right? Using ratio, find initial, find final. Then we using the ratio to find the new beam. New power of the new beam. Is it okay? Digest. And then tell me if okay, give me a reaction so we can proceed to the next question. Yes, good job, dear. Okay, if okay, then we goes to the next question, number 3. A train travels at a constant high speed along a straight horizontal track towards to the observer. Okay, the train producing the sound, this one not important. Actually, this one is one to ask for the Doppler effect. Okay, what we want is the second part. The sound has the intensity, I. Intensity. And then the wave are incidence at right angle on a circular. Circular. Okay, circular. Circular. And the radius is 2.8 cm. From here, what you want to count? The wave incidence at the surface. Right angle is 90 degrees to the surface. So this is what we told you just now at here. The area perpendicular to its motion. Okay, so at here, from here, actually they want you to calculate the area. The circular pi r square. Okay, so power AI is very powerful. This is called area. This is called intensity. Okay, so boys and girls, do your calculation. No, Wesley? Did you convert the cm to m? Do you convert cm to m? Because power in watt is SI unit. Yes. Power watt is SI unit. So don't forget all the things that you use must be in SI unit. So 2.x cm you should convert to meter. Yes, power correct. Washini correct. Wesley correct. Oh, okay. Area is pi r. R is 2.8 times 10 power of negative 2 square. Wait. Pi r square. Yes, pi r square times the intensity is 4.7 times 10 power of negative 3. So for our answer, if you press it correctly, 1.2 times 10 power of negative 5 watt. Is that clear? This one in watt is SI unit. That's why you also need to convert this in meter. Is that clear? SI unit. Is that clear? If okay, then we go to the next page. Anybody? Yes. Okay, so we go to your page number 3, question number 4. Okay? Let's go. Can you count intensity? Okay, I'll let you do by yourself. They give you the power from the diagram, what information you can get in order to calculate and using the power formula. Hmm. Wesley, the third significant figure. Wait, oh, okay, two significant figure can call. Okay, Wesley, okay. Okay, Fawa, okay. Kai Chen make it 2 to 3 significant figure, but your answer is correct. Washini correct. Okay, as I told you, power AI very powerful. Area, from here the area is actually, you have to convert it into meter. So at here 1, 2, 3, it will be 1.3. This one also 1.3. So area will be 1.3 times 1.3 times your intensity. We don't know. The power is 750. So I add here except 440 watt per meter square or 444 Wm negative 2. Okay, is that clear? Kaichen, correct. Remember, don't forget about the unit. Although here is writing lah, okay? If they are not writing, you have to write the unit. Okay, another square solar panel is placed. This one is quite challenging question. Now you have to think. Another square solar panel is placed so that the light of the same intensity is incidence normally on it. The new one has a short side. Okay, let's say just now at here we got 1.3 times 1.3. Now they tell you that we got a new one. But new one maybe is only like 0.6 meter and 0.6 is smaller. But they both are receiving the same intensity. Same intensity will be received. Okay, they're producing same output. Same output power. Okay, both producing the same output power. What do you think about which one is more efficiency? The new panel actually efficiency is greater, less, or same? What do you think? Think. Both were providing you same output. Then the first one is we're using a greater area. Second one we're using smaller one. Which one more efficiency? Wesley, correct. Have a look, Kai-Chen. Kai-Chen, no. Kai-Chen, no. You think you need a bigger one or smaller one? Both are producing you same output. Fawal, no. Jore, correct. Okay. Okay. Here, you have to think same output efficiency. Okay, maybe I can talk about efficiency. Efficiency is output divided by input times 100%. Am I right? Am I right? Correct. Then this one output is constant. It's the same. Same. Okay, it's the same. Am I right? So input at here, the input that we get, okay, input equals to A times your I. The area at here, input actually is bigger or smaller for the second case. It becomes smaller, am I right? That means that the input that I get is actually small value, smaller value for the second case. But I still getting the same output. What is my efficiency? My efficiency actually is higher. For second case, or you can think in this way, this is theoretically explained to you. P equals to AI. The area is small, so actually the input that I get is less input. But I still producing a very same output as you. For example, you need a larger area only can produce this output. But for me, I can using half of the area. I also producing the same output as you. So I'm so efficiency. I'm small, but I can produce same output as you. I receive less, but I produce a lot out. I can produce same output as you. So do you get the idea of this? If in theoretically, we can think in this way, P equals to AI. My area becomes smaller area. So the power that I receive in input is actually small. This one is a small value. But my power output is the same. So a value divided by a small value, your efficiency actually become higher. Or if you still cannot, then we have to put some value. If let's say the power that we get is 750. 750 watt. 750 watt. Maybe at here, this one. I receive 1500. Okay, for this case, My output is 750. My input that I get is actually 150 times 100%. My efficiency is only 50%. Okay? So for the second case, my output is 750, but my input that I receive for the power actually maybe only like how many? 1000, for example, 1000. Okay? Times 100%. So at here, 0 cancel. So this one cancel. My efficiency is 75%. If you still cannot, then I have to use number to show you. Can you see that my input power, I only receive 1000 because my area is small. My power that I get input is actually only 1000, but I can producing 750 watt. Do you get my idea, dear? Did you get my idea? Ask me question faster before I proceed. Any of you? Oh, this one it may be 750 is not 750 times 100 divided by 1500. It's 50%. Yeah. It's 50%. None of you got question? You don't have question. I don't know that whether you understand or not. Whether I explain clearly for you. Smaller ones is more efficiency. Yes, Kai Qian. I small, but I produce same as you. Okay, I produce same output as you. Understand, Fawal? Thank you. Wesley, how to write it? Okay, so if you understand, then we can continue this part. Efficiency, area of the new panel is less. This is 1 mark. Okay, input power of new panel is L, is less. Okay, and then here output efficiency. So efficiency is greater than original panel. I'm small, but I can produce so powerful like you. I don't need a much area, so big area. Small area also can producing same output as you. So actually, I'm more powerful. Is that clear, dear? Okay. If no question, we are going to the question number 5. How about others? Only Fawal said okay. How about others? Okay, then I proceed. I proceed. Next. Parallel light ray from the sun are incidents normally on the magnifying glass. So this one at the center here, this is magnifying glass. Magnifying glass will help us to convert, okay? Direct the light to an area. So this is the area of radius out. Magnifying glasses is the circular in cross section with a radius 5.5. Oh, okay, this is 5.5. The intensity light from the sun is incidence of the, okay, this is I. So we label this is I. Assume that all the light incidence on the magnifying glass is transmitted. Oh, all the light will going to this area. All the light later on will goes to this area. Okay, then after that what? Calculate the power. Power equals to AI. Okay. Do you have I? Yes. Do you have A? Can you calculate the area on the magnifying glass? Okay, do your calculation. Tony, do you able to follow, Tony? Jahan, Fatima? Bộ Yang ấy, Bộ Yang. Vashini, correct. Good job. How about others? This is circular. Like circular. Circular, the area will become pi r square. Times your intensity 1.3 times 10 power of 3. Don't forget the prefix. In A level, prefix is like normal things. You have to know how to do conversion. So at here, your answer should be 12 watt. It should not be a problem, right? 12 watt. Vashini correct. Wesley correct. Kai Chen correct. Bo Yang, yes. Okay, Bo Yang is here. Okay, power is equals to AI. AI is very powerful. 12.4. Oh, no problem. I think it's just I round to two significant figure. If you after you do calculation 12.4 also no problem. 2 to 3 significant figure. Okay, the value of R. Now the light going to here, okay, this area. And then they say that all the light will be transmitted to this area. So at here, your power will be transmitted down, going down, okay? So at here, intensity power equals to AI. Now your area becomes small. Area becomes small. But the power is the same is because just now this sentence tell us. The power go there. So can you tell what is your new intensity? Wesley, are you forgetting something to convert? Kai Qian. Kai Qian is positive or negative? Times 10 power of positive or negative? All the magnitude is correct, but that is positive. You try. Is it which part you make mistake? Washini correct. Power is 12. Area is pi r milli. So it's 1.5 times 10 power of negative 3 square. 3 square. But I did convert. You convert. Then we check. For one, make it two significant figure. Intensity I. So if you do it properly, it should be 12 divided by pi 1.5 times 10 power of negative 3 square. Just now, who was that? Let me have a look. Wesley correct. Kai Chen correct. Read it wrong. Read calculator wrong. Okay. So boys and girls, here your answer it should be 1.7 times 10 power of 6 watt per meter square. Is it okay? Yes or no? I haven't taken attendance today. Vito not here, Bo Yang here, Kai Qian here, Yue Ting not here. Okay, let me take attendance first. Vito not here, Yue Ting here. Yue Ting here, is it? Yue Ting no. Kai Qian here, yes. Okay, so boys and girls, we go to your next page. Loudspeaker, microphone, okay, and CRO arrange. So we combine the idea, okay, the knowledge that we learn. The loudspeaker is emitting a sound wave which is detected by the microwave. Intensity in B, okay, intensity for this case is reduced to quarter, 1/4. So that means that your new is 1/4 to your original intensity without changing the frequency. If you didn't change the frequency, that means that your period is constant. Period is the same. Okay, assume that the amplitude received by CRO is proportional to the amplitude of the sound wave. Okay. Sketch the trace that is now seen on the CRO. Okay, here we want to draw and sketch a new wavefront. Now we got two information. Periods are the same. So that means that we will get exactly the same. Okay, from here, 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 here. Just we don't know that the amplitude only. So you have to relate the intensity and the amplitude. Okay, new amplitude in terms of original amplitude. So you need to do the same thing like just now. Okay, initially is Ka square. This one is original. Okay, then new one new is actually Ka. Oh wait, oh new is 1 over 4. K, okay, it's okay. Ka square. Okay, Ka square, but this one is new A. Okay, new A. Then after that, I new divided by IO is actually Ka new square divided by Ka square. Okay, here I new over IO actually is 1 over 4. Do you agree? I new from here. I new over IO is actually 1 over 4. Do you agree? K and K cancel. Okay, I want you A new square over A square. Original A. Original A. In terms of A new, can you tell me how many AO? Do it. Continue it. So we need to find initial, find the final. We only can know what happening with right now the new one. I want to know the amplitude in terms of intensity, so I have to use this formula. Okay, so I new over IO actually is 1 over 4 from the sentence. Intensity of new B is reduced, so it's 1 over 4. Is it 1 over 4, Wesley? No. Farwell, correct. How about others? You're correct. Wesley, correct. So this one, actually you will get A new over AO because this is square. So we have to square root 1 over 4. So at the end, you will get 1 over 2 AO. So today we did three questions, similar question, finding the new power or new intensity in terms of their original one. In terms of their original one. If this kind of question, we're using ratio to solve it. We're using ratio to solve it. Okay, so at here, so from here to here, can you help me to read how many box? How many cm? Not box, how many cm? Read for me, how many cm? Three cm? No, Kai Chen, you didn't read it properly. Correct, Vashini. Fatima, read it properly. How many box? 1 cm is 1, 2, 3, 4, 5 box. 1 cm is 5 box. So 1, 2, 3, 4, 5. This is 1 cm. 1, 2, 3, 4, 5. This is 1 cm. So here is already 2 cm. Okay, 1, 2, 3, 4. Here is 4. Here is 4. So it should be 2.8 cm for the amplitude, original amplitude. So right now, your new amplitude, it should be 1.4, half of it. So you should be 1.4. So 1.4, we have to count. 1.4 is here. 1.4 is here. Bottom part, 1, 2, 3, 4, 5. 1 cm, 1, 2, 1.4. So it's here. Is that clear? So we continue to draw the wave front. Then going down, going up. Then continue going up, going down. Then continue. Okay. This is my new wavefront. My new wavefront, yeah, this is new. Frequency is the same, but my amplitude become half of it. So from here to here, I become new amplitude is actually half of original, so it's actually 1.4 cm. Is that clear? Yes, very good. Okay, when we do more partial question, we'll know that the pattern and we'll know how to solve it. First time when we try, maybe we don't have the idea that we can using the new one divided by the original one. But today we did 3 questions. In terms of the original one, what is your new intensity or what is your new power? Okay, so the idea is the same. We find the initially and we find the new one. So we make a ratio. I will know that the new one actually in terms of the original one actually is what is the relationship. Okay, is it okay? If okay, we are going to the next lesson. Nobody respond. Oh yeah, Fawal say yes. How about others? Prasan okay. Vashini okay. Kaichen okay. Fatima okay. Wesley okay. Tony okay. Mana Prasan? I simply call only. Okay. 28 longitudinal Prasan is here. Okay. So boys and girls, just now we got talk about progressive, we got longitudinal, we got the transverse run. Okay, so this one is actually nothing for you to feel is because this is year 10 knowledge. This is year 10 knowledge when we learn about wave, okay? So the particle is perpendicular, which is 90 degrees to the direction of wave. Okay, longitudinal is parallel. The particle vibrate in parallel way with the direction of wave. But no matter which one, the particle at here, they won't travel away. Let's say you type some color at here. You are finding that this color ribbon, it just move up down, it won't go away. It will be here. If you type somewhere here, also the same. It will move left, right. But at the end, it's still at there. Okay? So this is the meaning that we say that wave transfer energy but do not transfer the matter. Okay? So we will create few region. One is called crest, one is called trough. Crest to crest is one complete wave. Trough to trough is one complete wave. Okay, the amplitude we can get also from the pattern. Okay, so transverse wave, for example, water wave, light wave, EM wave. EM wave, we got 7. Radio wave, microwave, blah, 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 until X-ray, gamma ray. Okay, for longitudinal wave, we will form 2 regions, compression and rarefaction. Compression to compression is one complete wave. Compression to compression is one complete wave. Rarefaction to rarefaction is one complete wave. The example is sound wave. Okay, so this one is just recall your knowledge. We go to your page number 2. What we are going to learn is this. Okay? So we will have 2 graphical representation. One is called displacement distance graph. Another one called displacement time graph. Okay, they are different. They are different. So displacement distance actually is displacement of particles, S particles. Different particles at different position. For example, student in the classroom is 30. I capture 30 students right now at this moment. At one instant, that means at this moment, at certain moment, t equals to maybe 10 seconds, t equals to 0 second, I capture all the particle, where is their position. This is called displacement distance graph. Okay, displacement time graph is I only observe one. I only observe single one. Then I record it down the time from time, from 0 second to 60 second. How it move. For the certain particle, how it move. It move up, down, up, down. I observe it and then I plot the graph. Like I observe 30 students, but I observe one of the students. I observe Jore only. How Jore move, how Jore walking, something like that. So at that, I plot the graph, displacement time graph. At time equals to 0, Jore standing at the door. 1 second, go back to the seat. Then another 1 second, where is him? I observe one particle. I observe Jore only. That is called displacement time graph. Okay, observe one. But displacement distance graph is I using camera capture. I capture all the 30 students. What is their position at this moment right now? So you get the idea? Did you able to get the idea? Okay, displacement distance graph is observe a lot of particle and their currently position. Displacement time graph is I observe one only, and then I record it down. How is the position from time to time, from 0. Wait, can you repeat it? Okay, Prasan asked me to repeat. Okay, but graph, we got two types. One is called displacement distance graph, another one called displacement time graph. What is the difference at here to represent our wave particle? For the displacement distance graph is we record the all particles, they are at various position. Okay, at one instant means at certain second. For example, at time equals to 0 second, I capture all the particle. So all the particle at here, this is one particle, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the particle at here, we got a lot of particle, and I capture their position right now. This is called displacement distance graph. Okay, so you can imagine is 30 students in the classroom. I capture using camera, capture. At the time that I capture, actually I recording down all the 30 students. So this is the things. At the moment I capture, okay, I record it down. Actually, I capturing all the particle at their various position. This is displacement distance graph. Displacement time graph is okay, displacement time graph is I only observe one particle. For example, I observe Jore in the classroom. How Jore? Just now is I capture 30 students. Some of them standing, some of them is sitting. I capture. Okay. But right now is I observe Jore only. So at time t equals to 0, then I found that Jore is standing. Then time equals to 2 seconds, Jore is walking. Times equals to 4 seconds, Jore is sitting. So for displacement time graph, I observe one particle, how it moves from time to time. So here, first one is observe all the particle. Second one is I observe only one particle. Okay, this one maybe right now we are still like don't know what is this, but later on when we do the exercise, we will be more clear. Okay, so later on we use the past year question helping us to get more idea about this. Is it okay? Okay, later on we use past year and then we come back to this idea again. Okay, here we got two wave, longitudinal wave or transverse wave. Okay, we will learn this too. If longitudinal wave, okay, if at rest position, so all the particle will have equal distance between each others. Okay, all these are particle. Okay, so at here you see I observe the particle, all the particle I observe. Okay, then here you see this displacement positive A, this displacement negative A. Displacement is a vector quantity. We need to have consider the direction, right? Okay, we can say that the positive area is they're moving to the right. So all the particle right now at here, positive area here, they're trying to move to the right. You see here, direction, they're trying to move to the right. Okay, so I can draw something like this. They're trying to move to the right. So when they move to the right, initially this is the point. They move to the right, it will become like this. The second one become like this, third one become like this, and then here. It's trying to move to the right. Here is positive A. So it moves to the right. Okay, when we goes to the bottom part at here, this area there, this area is going to the negative A. Am I right? Negative A. Displacement have to consider direction. So right now they're trying to move to the left. So you look at this position, starting from here, negative to here, they all particle trying to goes to the left. You see? They all trying to goes to the left. So when they're trying to goes to the left, this particle goes here, these particles go here, this one go here, this one goes here, it goes to the left, then this one comes to here, then this one comes to here, and this one comes to here. So boys and girls, when they move, positive A move to the left. Okay, then pause. Oh, sorry, I write in a wrong way, but it's fine. Actually, it's the same thing. Okay, positive A, I move to the right. Correct. Did I write right? Okay. The positive area will goes to the right. Negative area will goes to the left. Can you see that the particle right now, they no longer have equal space. So what the space they have at here, they are very packed. This is compression. So at this position, actually is compression. And then comes to this, you see again, this is a positive area part. So they're trying to the right. They're trying to goes to the right. Okay, they're trying to goes to the right at here. They're going to the right. Wait, here, goes to here, goes to here, goes to here, something like this. Okay, so at the end, you found out that this area is called rarefaction. The particles are far from each other. You see this particle surrounding is goes to the left, here goes to the right. They are far from each others. Then this one, they become nearer to each others. So here it become compression again. It's a new thing for you. It's new thing for you. I know it's not easy, but we try to understand. I repeat one more time. Initially, all the particle having equal space between each others. Okay, so this time graph showing what? What can it showing? Okay, it's showing that it will having travel in positive A. So we can say that positive A is moving to the right. So for this particle and in this area, they were trying to move to the right. So can you see that this particle goes to the right? Come here. This particle goes to the right, come here. This particle, it goes to the right, come here a little bit, come here, come here, come here. So at the end, when they go, we found that this area actually, all the particles trying to come here to the point, this point. Then here is negative area, negative displacement. Negative, that means that now the particle trying to in the opposite direction, moving in opposite direction. Just now they goes to the right now goes to the left. So the particle trying to compress and move to the left. At the end, this part, from left and right, they're coming together and compress in this area. They will pack together in this area. So this area actually is compression. In the displacement time graph, we know that this area actually is compression. For the first part, is it okay? For the first part, positive A particle all trying to goes to the right. Negative A particle trying goes to the left. So at the center middle here, actually the particle they are packed together. So this region from the graph, I know this region actually is compression. Until the front part, is it okay? Is it okay for you, dear? Okay, Fatima, okay, Vashini, okay, Fawa, okay, Wesley, okay. Okay, so this is the first part, okay? Second part, we want to find rarefaction area. So you found that second part at here is negative displacement. So in moving to the left, the particle trying to goes to the left. Then comes to here, positive displacement, it goes to the right. You see all the particle goes to the left, all the particle trying to goes to the right. So this area, actually the air particle is very less. Very less air particle at here. This is called rarefaction. Is it okay? So we try, we try. If you really can understand, then you can answer this question. 2023. Longitudinal wave is traveling from left to right. The graph shows the variation of the displacement of the particles. See, particles. They observe all the particles with distance along the wave at one instant in time. So maybe like at time equals to x second, I capture all the position of the particle. Displacement to the right we say is positive. So here, this is positive. So that means all the particle here, they're trying to go to the right. Displacement to the left is negative. So here they're trying to go to the left, opposite direction. Can you tell me which label point represent compression? Wesley, yes. The second answer is correct. Fawal, correct. Fatima, correct. Dear, is it okay? You get my idea or not from the displacement distance graph? Okay, all the particles they're trying to move. Okay, because they are in positive, so they're trying to move. So that means that here they're trying to move until this point. All the point actually they're trying to come here. So this point. Okay, this one is they're trying to go to the left, opposite direction. So they're also coming. Somewhere here. Can you see this part? The particle, they are close to each others. Okay, so here the particle, they are very close to each other because left and right, they're all coming here and compress at here. This is the compression. So answer is B. Where is your rarefaction? If I ask you rarefaction, can you tell me what is your answer? Washini, B correct. Kai Chen correct. Tony correct. Fawao, if rarefaction, I want to ask my question in rarefaction, what is your answer? Answer Fawao is correct. Kai Chen correct. Tony correct. Here, they're trying to move from this part is positive, goes to the right. So this part is that goes to the left, here goes to the right. The particle at here actually is rarefaction. Answer D is actually rarefaction. So boys and girls, do you able to interpret? Do you able to interpret from the displacement distance graph? Yes, Fatima, do you get the idea? Yes, okay, like boys and girls, we learn a little bit. We still got 3 minutes. We try, dear. Number 3. Okay, just now it's longitudinal, so they move left, right like this. But if transverse wave, they will move. Okay, they will move like this. Okay, perpendicular, they move. So we are direction of the particle motion by comparing the two wave fronts separated by a very short time interval. Okay, the dotted line actually is the wave front after a very short time. So we want to know where the particle will move. Okay, after a very short time, maybe 1 second or whatever. Okay, you will find that the original one, when they go to the next wave front, actually for this part, they were going up. Okay, here to the new wave front actually is going down. Is that clear? That's all. We slightly draw a little bit, like dragging a little bit after a time. Okay, so if you clear, then we comes to here. Let me have a look. What question is better? Okay, this is the one. Very important because I want to explain back just now you asking me displacement time graph and displacement distance graph. Okay, we look at this. Transverse wave on the root have a wavelength and period t. The graph show the variation of displacement of particle with the distance. So this one with distance, this is the observe all particle. They observe all particle. So here they're saying that a particle X is labeled this point. This particle. Now I only talk about this particle. Okay, what is the displacement of particle X? I only talk about this particle. So at here, time equals to time with time t. Okay, initially at here, this is the time. Do you agree? This is the time at t. This is the position of your x. Now, divide displacement over t. Actually, is I observe particle x only. I don't consider others particle. I just look at the x. So boys and girls, initially at time equals to 0. Starting from here, I trying to record in motion. So at time equals to 0, your displacement for your x is 0 because it's here, 0 here, 0, 0 is 0. So you look at here, which one is possible starting? B and D confirm wrong. B and D, they are not starting from 0. So B and D confirm wrong. We must start from 0 here. Until here, is that clear? Until here, is that clear? Okay, then after that, I'm going to observe. After the time, that means that I have to draw my pattern. Okay, I have to draw my pattern, something like this, slightly, what we say? Ooh, okay, wait I draw again. Slightly after a certain period. Okay, do you agree? This one is after a short time. After a short time. After short time. Okay, the wave will move to your right. So can you tell me here what's going on? After a short time, it should going down first. It should going down first. So at here, A and C, which one is the correct answer? Obviously, right? After a short time, it will go down. So that means that it should be going down. Here, it should be going down and then go up again. So answer should be C. Okay. Let me have a look. Fatima, is it okay? You draw the new wave front, okay, which is slightly move it to the right, okay, so that we can know that what is the next step for this graph. Then just now, is it Prasan you're asking me about to explain one more time for this? So with this example, do you clear about displacement distance graph and displacement time graph? Okay, understand? So displacement distance graph is a lot of particle, not only x. I got A, B, C, D, E, F, G, H, until Z. All particle at time equals to 0, I captured. So now I only observe particle x. I only observe particle x. At time, so I record its motion. So starting is at 0. So B and D confirm wrong. Then I want to know next motion. So I draw the wave, slightly move the wave to the right hand side. Then I found out that it should be next step, it should be going down. So answer will be C. Any question, boys and girls? If no question, then next we will continue with the past year question. No question, Let me have a look, Vashini. No question, thank you. Wesley, can repeat why is C again? Okay, Wesley. So wait, here. Okay, Wesley, do you able to accept B and D confirm is not our answer because at time equals to 0, it should be 0. So B and D, do you able to accept? Yes, Okay, then after that, Wesley here, I want to know how the particle x is moving after t equals to 1 second. For example, after t equals to 1 second. So what should I do? This is my pattern of my wave. Wait, here. This is my pattern of my wave. Okay. After a short time, this wave, it will move, slightly move. Slightly move like this. Do you agree? Slightly move to the right. It moving what? Okay, it will move. See, it will move. So it will slightly to move. Then when it move, we want to observe the particle, x particle, they won't be moved to the right. They just moving up, down, because this is called transverse. Transverse wave, transverse wave. the particle is only moving up, down. Okay, it won't travel along the wave. It's just moving up, down, up, down. So we want to know after t equals to 1 second, where is the x particle will go? We found that the new wave front, actually the x particle is here, x new position. So I know that it's actually going down. The x point after t equals to 1 second is going down. So basically, it should be going down first. Then after that, at a certain moment, it will come back to the positive. So it will go down first. The particle will go down, go up, go down. So it's going down, going up, and then going down. Now, Wesley, do you get the idea? The particle x at time equals to 0 is 0. Then after that, 1 second is going down. 2 seconds is still going down until the trough. Then going up, 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 and then go down. Like Wesley? Where does it go down? Where does it go down? Which point? Which point? Do you agree when wave moving, the x particle actually is moving down, up, down, like this? Or maybe up, down, up. Do you agree until here? Yeah. Okay, so at here, I want to know, it going down first or it going up first to complete the one complete wave. So I need to move my new wave, whole wave, I make it move to the right a little bit. So you can see this one. We move the new wave front to the right a little bit, maybe after 1 second. We will find that this particle, to the new wave, where is the position? Is actually here. So the particle actually going down first, then going up, and then going up, going down. So for us, actually it's the same thing for this. It will going down first. Then continue, you move. Continue, you move. Then you'll find that it will go up. Go up and then go back. It will go at here, going down, going up, going up, going down. But because time, so actually we stretch it out. Time 1 second, 2 second, 3 second, 4 second. At 1 second, it going down. Then another 1 second, it coming back. Another 1 second, it going up. Another 1 second, it going back again. So basically, the ribbon go up, go down, go up, go down. It keep on repeating up, down, up, down. So for us, x particles first start go down. So you going down until your trough. Then it coming back until your displacement is 0. Then it going up until your crest, going down until your 0. So at the end, we get this graph.